Welcome to lesson 32 of our friendly introduction to abstract algebra. In today's video and the next one or two videos we are talking about cyclic groups and their classification in depth. So first, the general definition that we also already have encountered several times before. A group G is called cyclic if it is generated by one of its elements. So it's called cyclic if there is an element, small x, lying in the group, such that the whole group is given by the cyclic subgroup generated by this element. Then the group is called cyclic. Okay. A few examples. The first classical example are the integers with ordinary addition. This is a cyclic group with generator 1 or -1 because now it looks a bit different here because we are in additive notation. So the elements of this group here in general are the powers x to the m, where m runs through the integers. Here, of course, 1 to the m is not what we want to write, because first of all, this would always be 1 if this were the normal exponentiation, but also because we are in an additively written group, so we write this here as m times 1. Okay? So what is m times 1? For positive m, this is simply the sum 1 plus 1 plus 1 plus 1 and so on m times. For negative m, this is the same sum but with a negative sign in front of the number. And clearly those are all the integers, of course, because this is simply the number m, where m is an integer. So you see that the integers are a cyclic group with generator 1, or of course you could also take -1. And this is an example of an infinite cyclic group. Now the classical example for a finite cyclic group with n elements are the integers mod n. So z mod nz, these clearly are generated by the residue class of 1 and they contain these n elements. 0 bar, 1 bar up to n-1 bar, and n bar would again give you 0 bar. This again is written in additive notation. If you want to have an example of a finite cyclic group in multiplicative notation, you could take the dihedral group dn and then simply take the cyclic subgroup generated by the rotation by 360 degrees divided by n. This subgroup clearly contains these elements: identity r to the power of 1, r to the power of 2, up to r to the power of n-1, and r to the power of n would be rotating the regular n-gon by 360 degrees, so you end up with the identity. This here I call Zn, not with a double line, but simply Zn. And shortly we are going to see that those are actually the only examples that exist. Up to isomorphism, a cyclic group is either this here or this here, and that's it. This is what we are going to show when we talk about the classification of cyclic groups. Okay, now we take a look at proposition 31, which contains some basic yet important properties of cyclic groups. First of all, cyclic groups are abelian. This is not so surprising. The proof is very simple. Then subgroups of cyclic groups are cyclic themselves. This is, I think, not as obvious. If you want to, you can pause the video and try to prove that on your own. And if G is a cyclic group and we have an epimorphism, so a homomorphism from G to another group H that is surjective, that is meant here by these double arrowheads, then H must be cyclic as well. And in particular, factor groups of cyclic groups are cyclic themselves. Okay, first we convince ourselves that cyclic groups are always abelian. So let G be a cyclic group generated by x, then any element of G can be written like this here, x to the power of m for some integer, which here, of course, I should also call m. and not K. So if I take two arbitrary elements, G and H, both can be written as x to the m and x to the n for some integers m and n. Now by a power rule that is valid in any group, this can be written as x to the power of m plus n. Here, of course, I can switch the order, so this is the same as x to the n plus m, and then I use the same power rule to write this as x to the n times x to the m, and this is h times g, so clearly cyclic groups are abelian. Okay, now we first prove number 3, and number 2 follows from number 3. Could have written that in a different order, but after I realized this, it was already too late. So let G be a cyclic group and H an arbitrary element of this group here. Now, phi by assumption is an epimorphism. That means it is surjective. So this here has a preimage under phi. And the preimage must look like that, x to the m for some integer m. So h can be written as phi of g, but phi of g is phi of x to the m. Now phi is a homomorphism, so this can be written as phi of x to the power of m. Yeah, here you can write this as x times x times x and so on, and apply the homomorphism property several times to end up with this here. So this means any element of H is of the form phi of x to the power of m, where m is an integer, and this clearly shows that H also is cyclic and phi of x is a generator of H. And now here, this assertion follows simply from the fact that the canonical projection from G to a vector group G mod n that sends an element to its left coset is an epimorphism. We proved that and used that several times. So this is an epimorphic image of G, and we just showed that then it also must be cyclic. So now finally we want to prove that subgroups of cyclic groups are also cyclic. This is a nice general argument. So let G be a cyclic group generated by X, and let H be a subgroup of G. So first of all, we consider the homomorphism phi sub x that goes from the integers to G and simply sends an integer to the mth power x to the m. Then we did this long time ago, but you could do it yourself again. Make sure that this really is a homomorphism. This follows from a power law in the group. And it clearly is an epimorphism because G being cyclic means exactly that all the elements of G can be written like that, x to the m, where m runs through the integers. Then, because it's a homomorphism, the preimage of this here, this is a subset or a subgroup of G, is a subgroup of Z. We proved in general that preimages under homomorphisms always are subgroups. And now comes the important observation. Subgroups of the integers are always cyclic. They are always of the form n times z for some integer n, which is exactly the cyclic subgroup of z generated by n, because those are all these sums here. N plus n, for example, is 2 times n. And this we proved a long time ago on some exercise sheet. I didn't look it up. Yeah, I just looked it up. It was actually problem set number 5, the last exercise there. There we proved that all the subgroups of Z must be of this form. And this was not an easy proof, at least for beginners. So now H can be written as phi sub x applied to the preimage of H under phi sub x. And this is true because phi x is surjective. For any surjective map, this here holds true. And then we just prove, because phi is an epimorphism, that it's the image of a cyclic group, which we know here, is cyclic as well. So this is a very neat argument, I think, to prove that subgroups of cyclic groups are always cyclic.